Hello, welcome to our channel again. Suraj here. And in today's video, the topic is going to be on the Rayleigh-Jeans law. So generally, in a previous video, we have discussed about some of the experimental results of the Blackbody radiation curve, which is generally the Wien's displacement law and the Stephen-Boltzmann law. And now we are going to discuss about the Rayleigh-Jeans law. So this law was developed by Rayleigh and Jean. And this particular law only quite well agrees at low frequency. It means at longer wavelength, this particular law is good. But at shorter wavelength, it means at a high frequency, this particular law fails out. And that's we are also going to study in this video that how at shorter frequencies, it means very high frequency, you can say that this particular Rayleigh-Jeans law fails. So this will go into today's video. So let's start our today's video. So before studying the Rayleigh-Jeans law, you have to understand the concept of the standing waves. But why we have to understand the concept of the standing waves and what is the link between these standing waves and the black body radiation, all that things. So to understand it, so you have to think like that. Let's suppose there is a cube here. So let's suppose there is a cube and I heat this particular cube. So what will happen? So it is a metallic cube, so there's a free electrons and the electrons are starting moving. So what will happen if it started moving or let's say oscillating? So if electrons started oscillating, they started emitting the electromagnetic waves in all of this particular, let's say X, Y, and Z axis. So if they started emitting the electromagnetic radiation, they started making the standing waves pattern and standing waves, and that's why exactly this is very essential to understand the standing waves while deriving the Rayleigh-Jeans law. So to understand this, let's say an example that here I've also made that when you heat it, there is electron vibration which produces the electromagnetic wave, and this particular electromagnetic wave that is produces this standing wave. So how a standing wave is made? So there is a very typical example to show that how exactly a standing wave is made. So it's like that when the two waves interferes with interference with each other, they form a standing waves. That's the typical formation of the standing wave. Like there is a very simple demonstration of the standing wave that you tied a rope from one end and one in your hand and you started weaving the rope, then there's a standing wave pattern. So that's exactly what the standing wave pattern is inside this particular cavity of this cube. So let's understand this, that why the electromagnetic wave is not on the walls of the cube. Yes, on the walls of the cube, there is no any type of electromagnetic wave. The electromagnetic wave is only this particular cavity in this particular space, not on the walls of this particular metallic surfaces. Why so? Because it's like that this is metallic wall when produces the electromagnetic wave, the atoms or electrons arrange themselves in such a manner that they just cancel out the electromagnetic wave so that the net electromagnetic waves inside this particular metallic surface is zero. And that's why the sides of this particular walls of this particular cubic wall, there is a zero, there's no any type of the electromagnetic waves, so it is no any type of the standing waves pattern in that particular side of the cube. It's only in the cavity of this particular cube. So hope you understand that what's the use of the standing waves here in the Rayleigh-Jeans law, as there are different types of waves. So inside the cavity, maybe the two waves from the different directions started superposition. You can say that interfere with each other and formations of the standing waves. And that's the way you can derive the Rayleigh-Jeans law using the concept of the standing wave. So let's start the concept of the standing wave. So, and we all know that the nodal points of this particular standing wave is from 0 to A, where 0 to A, where A is the side, A side is the of a particular cube, and the nodal points of this standing waves are 0 to A, and like that, this is your first wave, and maybe this is your third wave, second wave, and exactly that. So the nodal points are on the sides of this particular cube, of this particular standing wave. So now let's demonstrate some of the mathematical formulation of the standing wave. So now here, we all know that the wavelength L of the standing wave is equals to the 2a divided by n, where n is any of the positive integer. So I can convert this into the form of lambda is equals to c upon frequency. Here v is mu, here is mu. Do not misinterpret it with the velocity. C is equals to the 2a upon n, where a is the length of the side of this particular cube. It means the allowed frequency. We can tell that the allowed frequency in this particular standing wave is equals to the nc divided by 2a. So this is the total number of allowed frequency of the standing waves inside a metallic cube. So here this is your allowed frequency, and where n is any positive integer which can be 1, n is equals to 0, 1, 2, 3, 4, and all that thing. So, but it all only takes the positive integer value. So this allowed frequency is called the mode of vibration in the standing waves, that these are the allowed frequency. And for each allowed frequency, there is an standing wave inside this particular metallic cube. So let's find out the metallic cube, inside the metallic cube, that's how many standing waves are forming inside a metallic cube in the frequency range. That what exactly you have to find. It means our second step is going to be find out NV. D means mu, it's generally. So our main motto is to find out that how many standing waves are there in a particular frequency range of mu to mu plus d mu. Okay, so this is 2, okay, not plus, so this is 2. So how many standing waves are there in from the frequency range of mu to mu plus d mu? And that what exactly this notation means. This is the means the number of standing waves in a particular frequency range of d mu. And that exactly what we have to find. And if we can find out this particular thing, then easily we can derive the Rayleigh-Jeans law, which gives the energy density of your particular, or you can say that intensity. We are more dealing with the energy density than the emissive power, because energy density is widely used than the emissive power. But yes, emissive power is also right. You can write this in terms of lambda, but generally we are writing this in terms of the volume, or you can say that in the terms of the NV, which is the energy density. You can also write down, there are two different alternative forms of the Rayleigh-Jeans law, which is in the form of the lambda. You can also write it, and in terms of the frequency, you can also write out your particular Rayleigh-Jeans law. So we have to find out the number of standing waves in a frequency range mu to mu plus d mu. How we can find out? So let's see here. Now we are going to derive. So now can I transform this particular form as n is equals to 2 a upon c mu, where n is the any positive integer, and for any n that corresponds to a particular frequency mu. So this is the one-dimensional case. What will happen, because we have to deal with the three-dimensional case, because cube is a three-dimension, so we have to derive this particular n expression for three-dimension. So for three-dimension, it is like this. So first of all, let's convert this particular form into more general form, that n is equals to the 2a, and in lambda then we are going to write it out 2a upon lambda x. So in an x direction, it is equals to 2a divided by lambda x, and it is equals to the, if you remember that the wave vector k is equals to the 2 pi upon lambda. So kx is equals to Lx 2 pi upon lambda x. So we can substitute 2 upon lambda x as kx divided by pi. It means this further can be written as nx is equals to the 2 upon lambda x can be written as kx a divided by pi. Okay. This is for nx because you know that we are going dealing with the three-dimension case. So we have to take the positive integer value nx in x direction, y direction, in z direction. So for x direction, this is like this. And similarly for y direction, it is 2a divided by lambda y, which I can write it as ny is equals to the k y a divided by pi. And similarly for nz, and z, it is equals to the 2a upon lz. L is the lambda, not the length, okay? L is the lambda. And z is equals to the 2, sorry, kz a upon pi. So this is a consequence. Now what we are going to do, we are going is squaring. So if you do the square, it's like this. Nx square is equals to the whole, this thing is square, and this particular thing is square. This is y. Okay, this is y. Square is this particular square, this square, and then this particular quantity square. Now we are going to add this particular three equations. So if we let's this particular equation as 1, this particular equation as 2, and this particular equation as 3, we are going to add this three particular term. What will happen is, let's see. So if we add this, it's like nx square. Okay, let me write in the code. Okay, nx square plus ny square plus nz square is equals to the kxa upon pi whole square plus kya divided by pi whole square plus kz divided by pi whole square. Okay, so next step what we can do is that nx square plus ny square plus nz square is equals to the, if I take common a by pi whole square, and here it's kx square plus ky square and plus kz square. So what's the meaning of this? So if you remember, it's equals to the k, where k is the wave. So k squared is equals to the, okay, so k square is equals to the kx square plus y square plus kz square. It means in the next step, we can write this particular equation as nx square plus ny square plus nz square is equals to the a by pi whole square into k square. And if you remember what k square is, so k is essentially equals to the 2 pi, 1 minute. So k is equals to the, k is equals to the 2 pi divided by lambda. So k square can be written as 4 pi square upon lambda square. Okay, now nx square plus ny square plus nz square is equals to the a by pi whole square and 4 pi square and upon lambda square. So I will put down lambda square as c square divided by mu square, which is c square divided by mu square. And in the next step, we can write this particular thing as nx square plus ny square plus nz square is equals to this pi square and pi square will cut out. It will become 4a square mu square divided by c square. Take here root under what will happen? It's like root under nx square plus ny square plus nz square is equals to 2a by c mu. Okay, so now here we have written our standing waves. It means in the three axes, which is nx, ny, and nz. So now if you look at this particular expression carefully, it's making some sort of a sphere, right? Because the expression of a sphere is equals to r square is equals to the x square plus y square plus z square. And similarly, in this particular fashion, this particular expression somehow is giving some kind of the experience of a sphere. Because as you look, this is similar x square plus y square plus z square. It means for the possible values of nx, ny, and nz, there corresponds a similar mu frequency. It means no matter what we are going to put your value of nx, ny, and nz, it will only give you the value of a certain frequency mu. It means if you put nx1, ny2, or nz3, it will give you the same mu frequency if you put nx as 3 and ny as 2 and nz as 1, just like in the case of a square, this in the circle, because in two dimension, the same expression r is equals to root under x square plus y square. So if I made a two-dimension structure like this, and let's say its center is right here, x square plus y square correspond to a radius. So if I imagine x coordinate as, let's say, 3, and y coordinate let's say 4. So if you do this square it, you will give that this particular expression is maybe here. Okay, so this is here. So this will be the radius. Okay, and it's no matter that if you put the value of x now 4 and y 3, what will happen? Then the particular diagram, maybe the points is here, and again this is the sphere, this is the radius of your particular circle. Just in the same case of this particular thing, in this particular sphere, for possible value of nx, ny, and nz, there is correspond to a certain frequency mu. Just like in this case, no matter what you put the value of, it means you can put the value of y as 4 and x as 3. Then you will get the same radius if you put y as 3 and x as 4. And just as if then the three-dimension case, this is the equation of the sphere. It means I will now make a diagram of a sphere in the, let's say, okay, so this is a possible diagram that I can make. This, let's say, z-axis, this is y-axis, and this is x-axis. But you all know that nx, ny, and nz, nx, ny, and nz can only take the possible values. It means if you know that in the three dimension there are eight, it means there are octants there, and we have to take the positive octant. So the positive octant lie here. So this is sphere, and here the meaning of this particular axis is that it is the direction of nx, it's the direction of ny, and it's the direction of nz. So nx, ny, and nz, and this is your corresponding frequency mu. So it's no matter of fact that what you put the value of, let's say here is 10, if I do the numbering, here is 9, here is 8, here is 7, or whatever this is, this particular nx, ny, and nz corresponding to a certain frequency mu. But again, remember, we have to find out the number of the standing waves pattern in a certain frequency. It means now we have to take a more bigger sphere. And this sphere now has a frequency of mu plus d mu. Remember this, that was the frequency of mu plus d mu. And we have to find out the volume of this particular region, because the volume of this particular region corresponds to the number of the standing waves in this particular region. An important conclusion here I'm going to write that the NVDV, which is the number of the standing waves in this particular region, this particular shell region, this, okay, this, because this is the bigger sphere and this is a smaller sphere in the first octant, because we only have to take the positive value, not the negative values. We all have to take the only the positive value of nx and y and nz. So we are taking the first octant, not any other octant. So in first octant, you have to find out the volume of this particular shell. And the volume of this particular shell corresponds to the volume of the is correspond to the number of the standing waves in this particular volume. So you have to find out this particular volume of shell. But why the volume of shell is equals to the number of the standing waves? Because if you think in the three-dimension case that the spacing between these particular n, the spacing between this particular n is 1. It means the cubes that are going to form here in this three-dimensional volume has a volume of 1, and 1 cube is equals to 1. It means the cube has a volume of 1. Small cubes corresponding to the every points on this particular shell has a volume of 1, such that if you divide the number of this particular volume with the volume of shell, it is similar. Because the area of this cube is unity, you can write this particular important conclusion that the number of the standing waves is equals to the volume of the shell. This is a very important conclusion, that the number of the standing waves is equals to the volume of the shell. Just let's say an example to explain this, that if you have let's say 4 cube, okay, so if you have a 4 cube, okay, and each has an 4 cube, or let's say square for simplicity. So if you, there's 4 square and each is in the side a is equals to 1. So what's the area of this particular 4 square? So yes, it is, let's say, meaning 1 meter, so it's 4 meter square. So if you can say that this particular number of squares is equals to the area of total area of this 4 squares. How? Because the area is unity here. And that's the same case in this three-dimensional case. Here in three-dimensional case, you can think that there are the small cubes are forming. For every ny, nx, and nz, there is a formation of a certain cube. And that cube has a volume of 1. And if the cube is a volume of 1, then if you find out the number of cube, then this is exactly equals to the volume of the shell. Just like in this particular case, if the area of this particular 1 cube is equals to 1 meter square, because its side is 1, and that exactly same case here, the small cubes of nx, ny, and nz has the volume of 1 units, whatever this is, meter, cube, centimeter, whatever this is, 1 units. Just like here in this particular square case, the area is 1 unit, and if you add the total area, it is 4, and this 4 is exactly equals to the number of the number of the, yeah, squares. 4 is the number of the square and 4 is also the area. And that the same thing we are going to do here. That the number of the standing wave in this particular volume, because if you certainly subtract this particular subtract this particular two spheres, so one sphere has an v plus dv and minus mu. So this and this will cut out, so you will get d mu. So we have to find out this particular volume of shell. So what is the volume of shell? So if we can find out the volume of shell, we can find out the number of these total standing waves in this particular volume. And then we can multiply it by the average energy to get the energy density. And then we finally look out our particular Rayleigh-Jeans law. Okay, so now volume of shell, how we can find out volume of shell? So if you remember the volume of shell, small volume of shell, let's say dV is equals to the 4 pi r square and dr. Okay, what's the radius? So if you remember here, radius is equals to 2a by c mu. So its square will be, so radius square can be written as 4a square divided by c square mu square, and dr can be written as 2a by c d mu. Then substitute these two values here, r square and dr. So now here dv is equals to the 4 pi, so the value of r square which will give into 4a square mu square divided by c square into 2a by c d mu. Now dv is equals to 416. Okay, so it's 32 finally pi a cube mu square d mu divided by c cube. But here remember what I have said now is that this is the volume of the shell. But we all only have to take the first octant of this particular shell. So we are going to divide it by 8 to get the actual volume of only this particular part, because here the area is for the whole. If you extend this diagram to a real 3D diagram, then this area corresponds to that particular 3D diagram. But only this area corresponds to when we divided it by the when divided by 8. It means this will become 4 pi a cube, a cube mu square d mu divided by c cube. So this is the total number of the standing waves. How? This is a volume. So what I've written here, the volume of the shell is equals to the total number of the standing waves. And why total number of standing waves? So I've explained here with the example of the squares that if each square has an area of unity, then the area is equals to the number of the squares. So just in the three-dimension case, this can be also true. And we are using this particular analogy to explain this particular effect. Now here, if I write it in a more good way, it's the formula which is the NV, V name mu, okay, mu. N mu d mu is equals to, this is the equal to sign, 4 pi a cube mu square d mu divided by c cube, but multiplying by 2. Okay, so why I am multiplying it with the factor 2? So if you have studied the polarization concept, you think that in a three-dimensional cube, if the electric field and if the standing wave is vibrating in the certain direction, let's say in the example of, okay, I have to make a cube here. So this is a particular cube. In the polarization, you have studied that polarized light, the polarized light electric field can oscillate in this direction and in this direction. This is the meaning of the polarized light. It means the electric field is only in one direction. This is the meaning of the polarized light. So in this case of the cube, for every given electric field in a certain direction, there corresponds to the electric field oscillating in one more direction also, and that's correspond to that why we are multiplying it with the 2. Because if you have studied the polarization concept, you know that what I am talking about. So if I multiply it by 2, then it will give the total number of standing waves. So NV, no, sorry, V no, mu, d mu is equals to 4 to the 8 pi a cube mu square divided by c cube d mu. So what here is a cube? So a cube is the volume of the cube. So now what I can take is that this is equals to 8 pi. Here capital V is the volume of the cube and it is mu square d mu divided by c cube. So this is the total number of standing waves. But this is not the complete part. We are going to derive the Rayleigh-Jeans law, which is for the energy density law. And how we can do this? So for this, we have to know the equipartition theorem. So what exactly is the equipartition theorem? So first of all, what I'm doing is that I am making this particular law in a more general form as number of standing wave d mu per unit volume is equals to 8 pi v square upon c cube d mu, because this is a good thing to do per unit volume. So this is the standing wave per unit volume in a cube, 8 pi mu square divided by c cube d mu. So finally, this is a very much more important thing, and we are going to use this particular important equation. So now we are moving to the equipartition theorem. So what exactly is the equipartition theorem and what's the uses here? So if you have studied the statistical mechanics, you may have familiar that when there is a random motions of a particle in the three dimension, then we divided, okay, so then we divide the energy of the particular particle. Let's say the particle can have a degree of freedom 2. It means it can move in x direction and the y direction. So we divide the equal energy in both the degree of freedom. It means E naught in this, E naught in yes, it's maybe true that in X direction, maybe the energy is greater, and in Y direction, it's lesser. But this equipartition theorem says that for a whole number, what we can do is that we can divide the energy of the certain particle in equally in this particular degree of freedom E naught, where this particular E is equals to 1 by half k T. 1 by half kT, where k is the Boltzmann constant and T is temperature, and that is a very important law that direct relationship with the temperature and the energy. So what we are going to do here is that to find out the yes, so equipartition theorem. So what's the equipartition theorem? Equipartition theorem for the one-dimensional harmonic oscillator, because we are dealing the electrons as an harmonic oscillator. They are doing the simple harmonic motion. So for a simple harmonic motion, it is 1D, but there is a special case. There is a special case. The energy for the one-dimensional harmonic oscillator, according to the equipartition, should be 1 by half kT, but no, it's kT. Why? Because in one-dimensional harmonic oscillator, there is also some sort of the kinetic energy which is associated with the momentum, and there is also a potential energy which is associated with its position, which corresponds to 1 by half kT plus 1 by half kT, and that leads to the energy, average energy of the one-dimensional harmonic oscillator is kT. And that is the equipartition theorem for the one-dimensional harmonic oscillator. So what we have done is that we have find the number of the standing waves in a frequency range d mu per unit volume, which is 8 pi mu square divided by c cube into d mu. So what we are going to do, we are going to find out the energy density. So how we can find energy density? So energy density, which U du, energy density is equals to the, and 1 minute. Okay, so energy density is equals to the n mu d mu divided by volume into the average energy, because this average energy is for the one-dimensional harmonic oscillator. So for if we deal the electrons, one electron as in one harmonic oscillator, So for every, if we have find out this particular number, so if we multiply out this particular energy KT, average energy KT, with the number of standing waves per unit volume, we are going to find out the energy density. What's the energy density? So energy density means the energy per unit volume. If you carefully see this particular term, it will gives you the total energy, and this V volume. It means this particular quantity is the energy density. So now, more general term, E mu d mu is equals to 8 pi mu square d mu divided by C cube and average energy KT. Now we are going to rewrite this in a more compact manner, which is U mu d mu is equals to 8 pi KT mu square divided by C cube. And yes, this is our Rayleigh-Jeans law. But here I've written in this in the frequency form. You can write this particular expression and you can change it into the wavelength form also. And okay, one more term is missing, which is T mu. Okay, now here we are going to now deal with some of the problem with this particular equation of the Rayleigh-Jeans law, which is very good, is that if you see this particular expression carefully, then the energy density, which is energy emitted per unit volume, U mu d mu, is directly proportional to the V square. Oh my God. So according to this result, if I take down all the things here, according to this particular result that it is directly proportional to the mu square, then the graph should look like this. Because it's directly proportional mu square, it means our graph should look like, if I made here the emissive power and the wavelength graph, and what I will, no, this is a wavelength graph. So for this, I'm going to draw the frequency graph. So the frequency graph should look like this. Okay. So let's say here is, okay, so let's say here is the U mu, which is the energy density, U mu d mu, and here is the frequency. So what's the predicting is that the quantum, which means the Planck radiation law, is predicting this result, that at low frequency it should like this. So it's increasing frequency, the energy density increases, but it has a peak at certain frequency, and after this peak it started going and goes to zero at infinity. But what here our classical law, which is the Rayleigh-Jeans law, is predicting that this energy should go to infinity. Yo, oh my God, no, this not. Graph should look like this. 1 minute. The graph should look like this according to the Rayleigh-Jeans law. But we all know that this is the correct graph. This is the correct graph, and this is the wrong, and that is the Rayleigh-Jeans law. That is your 8 pi kt divided by c cube mu square d mu, and that law is predicting that it should increase with the increasing frequency, but no, the observational experiments and all that things and the Planck radiation is predicting this particular thing, that at certain frequency it should maximum, and after this should good increase and sorry decrease and goes to infinity. And in infinity the frequency tends to zero. And that's the problem with the Rayleigh-Jeans law, that at low frequency you can think that at low frequency it quite well work, but at high frequency it blows down, and that is the drawback of the law. And that's the problem with it. And one thing more you can do is that if you integrate this term, including all of this particular frequency, what will happen? So integrating it from 0 to infinity, because there may be the infinity number of these standing waves there, this terms blows up to infinity, which again is the wrong thing. This means this is wrong. This is wrong, and this is termed as the so-called ultraviolet catastrophe. So-called ultraviolet catastrophe. That exactly is the ultraviolet catastrophe and the problem with the Rayleigh-Jeans law. So hope that you understand all of the particular derivation. The derivation is quite complex, but I tried my best to summarize the particular derivation. Hope that you understand that why I made the importance of these particular spheres and all that things, because this is very much a more important part. But if you found any type of the difficulty, you can write down in the comment sections any of the particular doubts. I will try my best to solve your doubts. And that's the whole video. Our next video is going to be on the Planck radiation law. And I'm giving you a hint that the problem actually here is with this particular term, which is this. The problem is this. Katie, yes, the equipartition theorem is wrong. And that is the hint for you. And in the next video, we are going to correct the average energy, which is the equipartition theorem in the quantum mechanics. It means for the quantum effects, this particular energy, which is the average energy, KT, is not correct. It's wrong. So next video is going to be the Planck radiation law, and it's also going to be very, very interesting that how the concept of quanta saves this particular experiment of the Blackbody radiation, as the classical equipartition theorem is quite wrong here. So that's all for today's video. Thank you for watching the video.